Okay.
Zoom is working better than just showing your presenter.
Okay. Well, yeah. So today I'm going to be telling you about sort of topic I've been interested in for the last few years, which you could whimsically describe as the study of quantum games, or like less whimsically as the study of many-body physics on quantum hardware. So just to start off by sort of motivating this, I'm a condensed matter theorist, and condensed matter is all about how more is different. And the traditional setting where we've looked for emergent phenomena is material systems. Yeah, so you have some rock and it displays some interesting phenomenon, and we seek to understand it. Now, in recent years, a new class of platforms has become available for us. And this is what I'll broadly call quantum hardware. So this could be systems of trapped ions, Rydbergs, superconducting qubits, neutral atoms. And all of these are platforms that are being built with a view to building quantum computers. Now, I'm not all that interested in quantum computers as such, but I think these are very interesting platforms in their own right as a new sort of setting on which to explore many-body physics and emergent phenomena. Yeah. And this is a sort of new setting which is very different to materials in terms of the kinds of states which we can prepare, in terms of the kinds of states that the kinds of things we can do, the kinds of measurements we can make. Yeah. So it's a very new sort of platform in which to ask all sorts of condensed matter questions. Yeah. And sort of fresh thinking is required to really have a good grasp of what the sort of many-body physics on this quantum hardware looks like. So yeah, so like one question that you could ask is there interesting new many-body physics to be done in this unusual setting? And this talk hopefully will be giving you at least proof of principle that there is indeed interesting many-body physics to be done in this context.
We should assume that quantum computers already exist.
Well, there are devices which definitely exist. Are they useful as computers? It doesn't matter. Yeah. So for the what? Because I'm not going to be using them as computers. I'm just going to be viewing them as devices to do interesting platforms to do interesting many-body physics. Yeah, I don't need the computer. Okay, so I should say that this work has been done with the following 4 individuals. This is my former postdoc, David Stephen, who is now permanent staff scientist at Continuum. This is Dominic Williamson at IBM. This is my current postdoc, Ollie Hart, who's currently on the market. And this is Michael Foss-Feig, who's also a permanent staff at Continuum. You'll notice 3 of the people on this slide have quantum industry affiliations, and that's because part of this work is done sort of in collaboration with sort of experimentalists, quote unquote, in quantum industry. I put experiments in quotes because we can sort of argue about whether these quantum devices should be considered experiments in the traditional sense or whether they're sort of unusual kinds of simulations. But whatever they are, there's actual devices on which you can do experiments, and industry has the best versions right now. So if you want to do experiments on these devices, then it makes sense to work with people in industry. Okay. So, coming back to doing condensed matter physics on quantum hardware. So what sort of questions might we be interested in? Well, one very basic kind of question that we might be interested in is whether we can define phases of matter on quantum hardware. Yeah, so you have some quantum device. Does it make sense to talk about it being in one phase or another? So, okay, I mean, we're not talking about thermodynamic phases of matter at this point. So we need to come up with some sensible definition of what it means to have phases of matter on quantum hardware. It's not a crazy project because after all, these are interacting very many particle systems. Yeah, maybe not Avogadro's number, but you could still have like a few hundred qubits maybe, and so then it's sort of sensible to ask about what sort of phase are they in, and getting rapidly bigger all the time. So the notion of phases of matter is not crazy, and whatever notion of phases of matter we come up with, though, it should have some like basic requirements. So the first is that it should be characterizable in terms of observable quantities. Yeah. And in particular, in terms of quantities which remain observable in the thermodynamic limit. So if your proposal for how you want to define phases of matter relies on post-selection, yeah, then that is exponentially costly in system size. You'll never be able to do it in the thermodynamic limit. And I'm going to complain that like that's not a valid definition of phases of matter. If your definition relies on entanglement entropy, then again, I'm going to complain that entanglement entropy is not a observable quantity. Yeah. That doesn't mean that post-selection and entanglement you shouldn't think about. There could be sort of useful conceptual aids. But at the end of the day, whatever definition you come up with should be able to be phrased in terms of observables. Yes, Fiona.
So on the entanglement entropy, so
Yep.
There are experiments that measure entanglement entropy, but here the point is that you need to do this data tomography stuff, and so you need a classical.
So, well,
Is that-
von Neumann entropy is not an observable.
Okay, bring
You can measure Rainy too. Yeah. That requires 2 copies in identical states with an orthogonality catastrophe problem. So it's still exponentially demanding on the fidelity of your state preparation. Yeah. So you can do it with 12, 16, maybe, you know, if you work hard and you have, and your Marcus Greiner. But no, I think even if your Marcus Greiner, you probably can't do it, you know, as your system sizes scale up. Yeah. The questions? Right. So no, it should be possible to express things in terms of observable quantities. And then the second thing is that knowledge of the phase the system is in had better provide us with some predictive power. Yeah. Because there's a particularly like trivial definition I could propose, which is that every initial condition I can prepare on my device is, you know, its own phase of matter, and that's a completely stupid definition, right? I mean, knowing that the system is in some particular phase should provide us with some predictive power about some universal properties, and those universal properties should be robust to some class of perturbations and noise and so on. Yeah? So these are sort of basic requirements for what we should demand from a sensible definition of phases of matter. Yeah, Tasha.
The finite size system does not need to survive in the thermodynamic limit. That would
No, I do want it to survive in the thermodynamic limit. Yeah. So I should have a definition. I mean, okay, current devices don't actually have Avogadro's number of qubits, but whatever definition I come up with is something that, you know, it should survive scaling to arbitrarily large systems. Yeah.
In this case, you know, you could have this phase of matter, I prepare some states, and then I'm probing that as a phase of matter.
Yeah.
Or I could have in mind some dynamics where, you know,
Right.
want something stable at long times. I
Yeah.
presume you're talking about the former.
I mean, I'll accept either. I'm perfectly happy to consider sort of dynamical phases of matter and sort of dynamical codes and so on. But with, you know, subject to the same requirements that there should be universal predictions which are robust and characterizable in terms of measurable quantities that scale. Andre?
But it's a predictable power in universal property.
Yeah.
And at the same time, it's not thermodynamic. Does it then depend on how much time you wait? That if there's small perturbation, but you wait for a long time.
Right.
That at the end of the day, there will be no universal property.
I mean, we may need to be careful about how we're taking our limits, right? But there should be some properties about which I can make predictions on the basis of knowing what phase of matter my device is in. And those properties should be robust to at least some class of perturbations.
No matter what time scale we're in.
No matter what time scale we're in, but with the caveat that maybe I'll allow myself to be you know, a little generous with my choice of limits. I mean, maybe I can take, maybe I don't need to take the T to infinity limit first. Maybe I can take some other limit first. Okay, so, you know, once we can define phases, then we can ask questions about phase transitions and how they manifest and so on. Yeah, and sort of pragmatically, we could also ask, if we have some sensible definition of phases of matter, does that have anything to do with the actual performance of the device and how well it does? Yeah. There's a different way you could view things, which is just to ask, okay, what are NISQ devices good for? Yeah, so like most of the people working, what NISQ, by the way, stands for noisy intermediate scale quantum. Yeah, most of the people working in this area are trying to build quantum computers. No, we're still very far away from having devices which can actually factor sort of large prime numbers or large numbers sort of competitively with supercomputers, much less do drug discovery. But, you know, never mind that. Like, there are devices, they exist, they're quantum. Is there anything that they can do clearly better than any classical system? Yeah. So is there any task at which they provide a clear advantage? And there's one strand of work in that field in quantum computing, which aims to demonstrate quantum computational supremacy. So you may have seen press releases by Google and so on about this. And the idea behind quantum computational supremacy is that you have some computational task, maybe not a commercially useful one, just a cooked up one for proof of principle, but it's a computational task which the quantum device is supposed to perform better than any classical computer. Yeah? Now, the problem with this approach is, well, twofold, but maybe the most basic one is that you're chasing a moving target. Yeah? So today you think you're doing better than any known classical algorithm. Tomorrow someone comes up with a better classical algorithm or a faster computer, and you're not outperforming anymore. So is there any task at which existing devices can unconditionally outperform? Yeah, like where the statement that the device outperforms any classical strategy is not dependent upon any particular set of classical algorithms, then it could not be invalidated by somebody coming up with a better algorithm tomorrow. So for this too, there will be an affirmative answer. And the way to answer all of these motivating questions that I've been posing is to go through something that I'll call quantum games. So quantum games provide an implementable and actually implemented approach to phase characterization on quantum hardware. They also provide a fixed target task at which already existing quantum devices can be shown to outperform any purely classical protocol. Yeah? And this is an unconditional statement, so even if you had an infinitely large supercomputer at your disposal, you could not do any better than the devices do. Yeah, the devices would still be outperforming. I will argue they also provide a powerful new perspective on many-body physics. Now, I should say, we did not come up with the idea of quantum games. This story has a long history. The idea of quantum games first originates in work by David Mermin of Ashraf and Mermin fame, decades ago, in a different millennium. And since then, many sort of luminaries have worked on this, including Fiona and coworkers recently, who wrote some very stimulating papers on quantum games, and we're certainly building on everything that has come before. Yeah? But okay, and I'm not, nevertheless, even though this is a topic with a long history, and even though one of the key practitioners is sitting in the front row, nonetheless, I think it's entirely possible. Oh, okay, who in the audience has seen quantum games before? Okay, yeah, so I should introduce quantum games anyway. So what are quantum games all about? So one way you can think about quantum games is as being sort of the intellectual descendants of Bell tests. Yeah. So Bell and Bell's inequalities demonstrated that quantum measurements can be more correlated than any local classical theory permits. Yeah. And this is the original observation which Mermin recast in the language of games, and that's sort of like quantum games paper number 1. So at that point, you could say, okay, this what Mermin was originally doing was just Bell tests, but recast in a different language. What's the point? It's the same old thing. And it has several advantages. One is that I think it's much more conceptually transparent than Bell tests. In fact, I would say that quantum games is probably the way we should be teaching Bell tests to our undergrads. But also it sort of scales and generalizes to many-body systems and complex tasks much more robustly than Bell's traditional formulation does. Yeah? So it's a language that's worth learning. So let me now illustrate how Bell's inequality works in the language of games. So here's the traditional setup for Bell's inequality. You have a Bell pair, let's say 0, 0 plus 1, 1, and the measurement outcomes on the 2 qubits are more correlated than any local classical hidden variables theory would permit. Yeah, that's what we teach our undergrads. Now, how do we recast this in the language of games? Well, the way to recast this in the language of games is as follows. You have 2 players, Alice and Bob, yeah, and Alice and Bob are going to be interrogated. So the way the interrogation works is like before the interrogation starts, they can discuss with each other, they can pre-agree on a strategy. If I get asked question A, I'll give this answer. If I get asked some different question, I'll give some other answer. So they can pre-discuss and get their story straight. But then once the interrogation starts, Alice and Bob are both led into separate rooms, yeah, and they're not allowed to communicate with each other during the interrogation. And the challenge is they have to somehow coordinate their answers, even though they're not allowed to communicate. Yeah? So in this context, what that means is that the interrogation is very simple. Each Alice and Bob is each given a single question, which consists of a single bit, 0 or 1, and they have to produce a single bit in response, which is also a 0 or 1. And the requirement is that the sum of the two answer bits should equal the product of the two question bits. Yeah. So can they accomplish this? Well, let's say Alice has a strategy which says, if I get asked question 0, I'll respond with YA of 0. If I get asked question 1, I'll respond with YA of 1. Yeah, that's Alice's strategy. Bob's strategy could be, if I get asked question 0, I'll respond with YB of 0. If I get asked question 1, I'll respond with YB of 1. Yeah, that's Bob's strategy. YA and YB for now can be just arbitrary functions. But these functions better obey the following consistency condition. Yeah? If either Alice or Bob gets given question 0, then their answer should add up to 0, more true. And if both of them get given question 1, then their answer should add up to 1, more true. Yeah? But now let's take these 4 consistency conditions, yeah, and let's add them up, mod true. Yeah? Remember, all of these guys are Boolean valued objects. Yeah, so y of 0 plus y of 0 is 0, mod true. Y of 1 plus y of 1 is 0, mod true. Yb of 0 plus yb of 0 is 0, mod true. Yb of 1 plus yb of 1 is 0, mod true. Yeah, so on the left hand side you get 0, and on the right hand side you get 1. Yeah, so contradiction. And that tells you that there is no possible set of deterministic functions YA and YB which can be guaranteed to satisfy all of the consistency conditions. Yeah, so Alice, there is no classical strategy with which Alice and Bob can be certain of succeeding. They could succeed by chance, but they cannot succeed with certainty. In fact, the best they can do is they can win 75% of the time, yeah, as Bell showed. As we know, if they have access to quantum bits, they can do better. So suppose that there's a entangled resource state, 0, 0 plus 1, 1. Alice holds 1 bit, Bob holds the other bit. And now their quantum strategy is the following. If Alice is queried with a 0, she measures in the Z basis and replies with her measurement outcome. If she's queried with a 1, she measures in the X basis and replies with her measurement outcome. And Bob does the same thing, except Bob makes a measurement in a rotated basis. Yeah. And now if you pick the angle of rotation optimally, then you can win with 85% probability, and 85% is more than 75%. Yeah. So if Alice and Bob are able to win this game with better than 75% probability, they're doing better than any classical players could ever have done, even if they had infinite computational resources at their disposal. Yeah. So this is Bell's inequality as taught to undergrads, but recast in the language of quantum games. You can view this either as you can use a quantum state to accomplish a certain classical task, and the better than classical performance tells us something about the underlying quantum correlations inherent in the few body state. Now, let me maybe ask you, what is it that makes a state quantum? Yeah, very basic question. Many people have tried answering it over the years. So if you open up the Feynman lectures, Feynman asserts that the thing that makes a state quantum is superposition plus discreteness of measurement outcomes. Yeah. So in the Feynman lectures, Feynman pretty much says that the whole mystery of quantum mechanics is contained in the double slit experiment. You do the double slit experiment, and if you do the double slit experiment with bullets, you always measure discrete bullets. There's no superposition of probabilities. You do the double slit experiment with waves. You have superposition of probabilities, but the measurement outcomes are not discrete. You do the double slit experiment with electrons. Measurement outcomes are discrete. You measure an electron or you don't, but you also have superposition of the wave function. Yeah. So it's this combination of superposition plus discreteness which sort of encapsulates the whole of quantum mechanics. Well, with all due respect to Feynman, that's an incorrect statement. You can get superposition plus discreteness in completely classical settings. In fact, there's a famous experiment by Yves Coudert 20 years ago, looking at sort of droplets of oil bouncing on vibrated films. which gets discreteness of measurement outcomes plus plus superposition of probabilities. So, in the 1970s, this answer was maybe state of the art, but in the 21st century, I would say this answer is just incorrect, not just incomplete. The answer we give to our undergrads nowadays, which I think is correct, is the thing that makes a state quantum is entanglement. Yeah? And you can talk about Bell's inequality as in violation of Bell's inequalities. And entanglement can be quantified in terms of entanglement entropy. And here's the canonical formula for entanglement entropy. Yeah. Okay, so here's entanglement entropy. It's a correct answer, but in some sense, entanglement is necessary for a state to be truly quantum, but it's not really sufficient. Yeah. So you could consider, let's say, a thermal state, a state with, where the reduced density matrix looks like a Gibbs matrix at some high temperature. That thermal state would have lots of entanglement. The entanglement entropy would be volume law, but there's basically nothing useful you can do with that. Yeah. So in some sense, even though that state has lots of entanglement, it's not really all that quantum. Instead, I would say the true, yes, Fiona.
I mean, isn't that just, entanglement entropy is not a great measure of quantum entanglement in mixed states, right? Like,
Okay, fine. Well, no, the state doesn't have to be mixed though, right? You could have, let's assume the eigenstate thermalization hypothesis is true. Let's pick a state out of the middle of the spectrum, right? It's a pure state, has tons of entanglement, like volume law entanglement. What can you do with it? I think basically nothing, right? So instead, I would say that the true answer to what makes a state quantum is contextuality. I'll explain what that means in just a minute. And for contextuality, entanglement is necessary, but not sufficient. Yeah. So the Bell state has entanglement and is contextual. The ETH state sampled from the middle of the many-body spectrum has entanglement, but it's not contextual. So what does contextuality mean? Well, a measurement context is a set of mutually commuting observables. So you could have Pauli X operators in qubit 1, Pauli Z operators in qubit 2, they commute. Pauli Y operators in qubit 3, like all of these are commuting observables. But in quantum mechanics, what you can have is that the outcomes of an Pauli X measurement on qubit 1 depends on whether you made a Z measurement or a Y measurement in qubit 2. Yeah. Even though measurements in qubit 1 and measurements in qubit 2, they're acting in different Hilbert spaces, the operators commute. Nonetheless, you can, if you have entangled states, the outcomes of measurements on qubit 1 will depend on whether you made, say, an X or a Z measurement on qubit 2. And this property is called contextuality. And like this, like quantum mechanics is incompatible with any sort of non-contextual theory. Yeah. And quantum games effectively directly probe contextuality. So motivated by that, let me now show you a different game, which will be more useful to us, and it's scalable, unlike the Bell test game that I showed before. So this is called the parity game. So the parity game is played by 3 players. Let's say Alice, Bob, and Charlie. And it's an interrogation game, same as before. So before the start of the game, Alice, Bob, and Charlie can all get together in a room and huddle and agree on a strategy. But then they're going to be led into separate rooms, interrogated. Interrogation will be to get a single bit as a question. They have to produce a single bit as an answer. They cannot communicate during the interrogation. And the win condition is that the sum of the 3 answer bits should equal the first input bit or the second input bit or the third input bit. Meaning, if any of them gets queried with a 1, then their output bits should add up to 1 mod 2. Whereas if they all get queried with a 0, then their output bits should add up to 0 mod 2. Yeah. Again, you can write down a sort of table of how the input bits are and what the output bits should add up to be. And you can write down a sort of list of consistency conditions. You can add them up. You'll get a contradiction. 0 equals 1. That indicates there's no classical strategy that can succeed at this game with certainty. As before, the maximum possible classical win probability is 75%. Yeah? You can win 3/4 of the time classically. So one way you could do that is they could agree, no matter what question I'm asked, I will respond with a 1. Yeah. And if you respond with a 1, no matter what, you win 3/4 of the time. But there's no classical strategy that does better. Andre.
0, 0, 1. Say 0 if B, 0 if C is 1.
Oh, so in this case, you're given the promise that the input bits always have an even number of ones. So either none of them gets a 1 or 2 of them get a 1. Okay, so what's the quantum strategy that succeeds? Now the state we want to use is, well, it's called the GHZ state, but you could also consider it just the the cat state of the Ising ferromagnet. So it's all zeros plus all ones, yeah? And each player is carrying 1 qubit of the state, and the quantum strategy is the following. If you're queried with a 0, you measure in the X basis, report your measurement outcome. If you're queried with a 1, you measure in the Y basis, report your measurement outcome. And this strategy wins with probability 1, yeah? So it's a perfect quantum strategy. And in some sense, you could say that this state is more contextual than the Bell pair, because the Bell pair only lets you win with 85% probability, whereas this state allows you to win with probability 1. More generally, if you weren't holding this state, if you were holding some state psi, and you use the same quantum strategy, you would win with the following probability, where M3 is called a Mermin polynomial, and in this case, it has the following form. Yeah? So the expectation value of the Mermin polynomial is at most 4. If you get expectation value 4, this adds up to 1. That's winning with certainty. You could do worse than that, but as long as you're doing, as long as you're winning better than 3/4 of the time, you're doing better than any purely classical strategy. Yeah? Okay. So yeah. That's quantum games with 2 players, with 3 players. Let's now go to n players. So you can generalize this parity game to the many-body context. Simplest version is due to Broussard, Boardbench, and Tack. So the setup is now you have n players, and they're given, each of them is same interrogation game for n players. Yeah, an even number of the questions will be 1, right? So the sum of all question bits is 0 mod 2, and the requirement is that the answer bits should add up to half the sum of the question bits, mod 2. Yeah. Again, there's no classical strategy that wins with certainty. In fact, in the thermodynamic limit, the best classical strategy wins with probability 1/2. Yeah. Yes.
In these games, you always choose a winning condition, right?
Yeah.
Now, is it possible to choose a winning condition, but classical strategy will give a better answer than one?
I mean, so let's take the games we discussed before, where the question was, can you choose games where the classical strategy will do better than the quantum strategy? Well, okay, you could do the quantum strategy wrong, of course, right? So, take the games I did before, right? If you could invert the quantum strategy and lose with certainty, right? Because if you can win with certainty, then you can definitely lose with certainty. But if you're asked, so that's one possible answer, but that's just you sort of being deliberately malicious and sort of doing the quantum strategy wrong. Yeah. Could you pick a game where the classical strategy allows for winning with probability 1, so it cannot be improved on? Of course you can, right? You could choose some trivial game where which can be won classically, and then there's no possible quantum advantage.
This is a non-trivial.
Right. So I do not think you can ever have a setting where the classical strategy does better than any quantum strategy could, because your quantum strategy could always be ignore quantum mechanics and just do everything classically, right? So at least you have to be able to do at least as well as the best classical strategy with access to quantum resources. The question is, can you do better with quantum resources? Yeah. And the point is, there exist games at which you can do better with quantum resources. Yeah. There also exist games where you cannot do better, but they're not useful for our purposes. Okay, so same game as before. In the thermodynamic limit, you win half the time. If you have access to this ferromagnetic cat state, all zeros plus all ones, then the same quantum strategy that I showed you before wins with certainty. Yeah. So you could view this as sort of harnessing the correlations inherent in quantum states in order to gain advantage at some fixed target task. Yeah. So if you have n players and they're able to win this game with probability better than 1/2, you know they're using quantum resources and they're accomplishing something that could not be accomplished in any purely classical setting, even if you had access to an infinite amount of computational power. Okay, so there's been very many other games that have also been discussed. But now what I'd like to discuss is like how robust is any of this, yeah? Because remember, I really wanted robustness as one of my desiderata. If something is particular to a very special state, and the moment you perturb away from that state, you know, the sort of physics goes away, you can't make any predictions, then it's less interesting, yeah? So how robust are these? Well, first of all, you know, if we want to characterize phases of matter, we need robustness. How much robustness do we demand? Yeah. So one possibility is like we want to be able to outperform the best possible classical strategy. By how much? So if you're satisfied with exponentially small outperformance, so you're doing better than the best possible classical strategy, but you're doing better by an amount that's exponentially small in system size, yeah, then how to do that is known. It was pointed out by Fiona and coworkers. Yeah. But let's say we're more ambitious. We want some advantage that survives to the thermodynamic limit. Yeah. So the amount by which we're outperforming the classical strategy should not go to zero as we make system size larger. Instead, we should continue to outperform the best possible classical strategy, by an order 1 amount, even in the thermodynamic limit. So if that's what you demand, yeah, then none of the previously discussed games accomplish it. So the previously discussed games outperform by an order 1 amount if you're given this exact state, like this exact cat state, all zeros plus all ones. The moment you perturb that cat state, you lose order 1 advantage, essentially instantly. Right? In the
Ising model case, you know,
Yeah.
you can set it up in a coarse-grained way so that as long as you have an order parameter.
Well, no, so in the Ising model, well, okay, first of all, if you allow for symmetry breaking perturbations, then you'll lose advantage at symmetry breaking fields which are exponentially small in system size. Yeah. Even if you enforce the symmetry exactly, you will have advantage, but it's this battle of exponential stuff that you guys talk about, right? Where you'll outperform the classical strategy, but by an exponentially small amount.
But we do have, you know, basically if you space your players out, right? So you want to do something coarse-grained,
Right.
then you have an advantage with, you know, scales with the order parameter, so it doesn't die in the thermodynamic limit, but it does actually, it dies a little before the phase transition, unless you change it.
Okay, I mean,
But yeah,
yeah.
this is not done.
Right.
Yeah.
Okay,
Not,
but
not,
no.
not with the long discussion.
So when you talk about
Yeah.
robustness or not robustness, you mean lazy, what do you mean?
Yeah, I mean, I want to allow arbitrary perturbations to the state. So, you know, you had some state psi. I'll allow myself to act on psi with any arbitrary unitary, which is close to 1, but, you know, some small noise perturbation, external field, and I want my outperformance to continue.
One question. So when you do this perturbation on the state, you also need to define the Hilbert space in which all other states with which you will be mixing. So is it important how you construct the Hilbert space? I mean, this effect of the action.
Yeah. Yeah, so for now, I'm considering a closed system setup, you know, where you have some quantum state and your perturbation could be some, you know, some operator. So, like if this, you could imagine it's made by some Hamiltonian and you allow yourself to add sort of arbitrary perturbation terms to the Hamiltonian, or you could imagine that it's prepared by some circuit and you want to allow for miscalibrations of the gates that were used, or, you know, some random noise that's snuck into the circuit. For now, I'm not sort of coupling in ancillas or anything like that. Yeah, so I mean, the question I'm interested in is, you know, can you get order 1 advantage that's robust away from the fixed point and is robust to arbitrary local perturbations, which, you know, I don't think is accomplished by any of the pre-existing games. So, you know, sort of as good condensed matter physicists, you know, we were raised to believe that the answer to how to get yes, Boris. No. Yeah.
You trying to see what kind of noise requirements?
No, I want to be able to tolerate any kind of noise.
Any kind of noise.
Yes,
Okay,
or any kind of unitary noise at least. Yeah. So, you know, as condensed matter physicists, we were raised to believe that the answer to this question is topological order. That topological order is the thing that's robust to arbitrary local perturbations. So let's try and use topological order. Yeah. So we're also not the first people to try using topological order. You know, Fiona and coworkers tried it. and they tried having the players measure sort of non-contractible Wilson loops, which wrap all the way around the system. The problem with that strategy is essentially to get orthogonality catastrophe. Yeah. So if your strategy is built around players measuring Wilson loops, which wrap the entire system, then that's fine if you're at the fixed point where you have the sort of infinite correlation length state. But the moment you perturb away from the ground state of the fixed point Hamiltonian, then your true Wilson loops get fattened. And you can't actually measure fattened Wilson loops. You can only measure bare Wilson loops. And the overlap between those two quantities goes to 0 in the thermodynamic limit. So it doesn't actually work. I mean, you have using topological order, but you're still subject to an orthogonality catastrophe. So our solution instead was to say that, look, the idea of using topological order is correct. That's what we want to be doing. It's the strategy that we need to change. Yeah. So we need to use the correlations inherent in topological order, because those correlations are going to be robust to arbitrary local perturbations, but we want to harness them in a way that is not subject to orthogonality catastrophe. And specifically, we want to harness them in a way that's somehow sort of locally probing. And the trick now is to use braiding statistics, because the braiding statistics are local probes of topological data. So let me illustrate how this works. We're going to be using the toric code. I assume everybody has seen the toric code before. Yeah?
No.
No?
Don't touch
Okay.
that.
Okay, well, Ising gauge theory, if you wish. Take the Ising model in 2D and dualize it, as Franz Wegener did. So here's the Hamiltonian. Qubits live on the links of the square lattice. Hamiltonian has two sorts of terms: product of z's around a vertex and product of x's around a plaquette. If you act with, so both of these guys are called stabilizers. This term is called the z stabilizer. This is called the x stabilizer. In the ground state, all of these stabilizers have eigenvalue +1. If you act with multiple stabilizers together, you end up making a loop of x's or a loop of 1's, a loop of x's or loops of z's. So the ground state consists of loops of x's and loops of z's. And in fact, the ground state of this Hamiltonian can be viewed as an equal weight superposition over all possible closed loop configurations of x's and z's. Yes, Andre. Pauli Z operator and Pauli X operator. In this Hamiltonian, so this is when the Hamiltonian is product of Pauli Z operators on the 4 links around a vertex, or product of Pauli X operators on the 4 links around any plaquette.
So it's 4 sigma.
4 sigmas, yeah. And the broader loop is product of Pauli X's, let's say, around any loop in space, where the lattice is not being shown, but like any arbitrary deformable loop, or product of Z operators, or sigma Z's around any arbitrary deformable loop. And the ground state is the equal weight superposition, over all closed loop configurations. If you have an open loop, then the endpoint of an open loop is an any-on excitation. There's 2 sorts of any-ons, E's and M's. And if you drag one around another, you get a minus sign. Yeah. So there's sort of non-trivial braiding statistics of E and M any-ons. So how does the toric code game get structured? Well, it's the same. Let's start with 3 players, and we can talk about n players later. So the 3-player version of this is the same parity game as before. 3 players, Alice, Bob, and Charlie. And their answers should add up to, or composition of the 3 questions. And what you do as before is that, depending on what operator what question each player is asked, they're going to make a measurement. Yeah. And they'll either make an X measurement or a Z measurement. So, Alice will either measure this X operator or this Z operator. Bob will either measure this X operator or this Z operator. Charlie will either measure this X operator or this Z operator. And you compose all of this together, and you conclude that essentially, you get non-trivial minus signs from this braiding phase between X and Z loops. And the bottom line is what you end up with is a perfect strategy for the parity game. Yeah. So if you have access to a quantum toric code resource state, and the players use the following strategy, where they measure these sort of loop segments of either X's or Z's, according to whether they queried with a 0 or a 1, then they win the game with probability 1. So toric code ground states are a resource state for the GHZ game. And the way we're using it really is we're using the non-trivial mutual statistics of the E and the M anyons. And this can be generalized to
non-local game that was played before.
Yeah.
And this one is that previously you're measuring Wilson loop all at once.
yes.
Now you're still measuring a Wilson loop normally, but you're doing it in stages.
But no. The key difference is that previously you were measuring non-contractible Wilson loops
Oh, okay.
of
So
size
they're-
L, and here you're measuring little loops, but just structured so they interlink.
Okay.
Yeah. So, and the key point is that what you care about is the overlap between the bare loop operator, which you can apply, and the true loop operator for the state, right? And that's exponentially small in the length of the loop. So if you're using non-contractible loops, it's exponentially small in L. But here it's just suppressed by some order 1 factor. Yeah, so you can do this with n players as well. I mean, it scales to arbitrary n. But what I was trying to assert was robustness, yeah? And I haven't shown you anything about robustness yet, so now let's talk about robustness. Sort of intuitively, it should be obvious that topological order is robust to arbitrary local perturbations. The braiding statistics don't change, so the strategy should continue to work, even if you deform. But nothing is as convincing as actually doing it and showing that it works. So we did it on the actual device and showed that it works. And now let me show you. Yeah. So we want to be deforming the state. Now, how do we want to deform it? Well, we considered a particular class of deformations, which is this one. This class of deformations, both because it's easy to analyze analytically and also because it's easy to implement on the device, but we think the results are valid for arbitrary deformations. And what this corresponds to is you take this equal weight superposition and you make it an unequal weight superposition over different closed loop configurations. Yeah? And there's a nice way to implement this on the device, which maybe in the interest of time I'll skate over, but basically we're using combination of weak measurements and feedback. So it's known how to make these sorts of states and these deformed states on this device. And you can do that. In fact, incidentally, you can sign up for this Oak Ridge program where you get credits to run on these devices. And it's sort of very user-friendly. It's just, this is a device which sits, in Quantinuum's lab somewhere, but you just log into it online and you say, please run the following circuit. And they just do it and they hand you the results. So, I can play it being an experimentalist without ever having to touch an actual device.
What was the device?
So it's a trapped ion based device, but I have never seen it. Yeah, I have experimental data on this device, but I have never laid eyes on it. So, yeah. So, okay, so this is an illustration of the circuit which can do this, and this circuit can actually tune you across a topological phase transition and constant depth because you're using measurements and feedback. And now here's the experimental data. Yeah, experiments in quotes because you can maybe argue it's not an experiment in the traditional sense, but it's some quantum device and you can do something on it and get results. So there's 2 panels here. So the left-hand side is we're trying to play the game with a sort of symmetry breaking all zeros plus all 1 state. Yeah. The right-hand side is trying to play the game with the toric code resource state using this topological strategy that I just described. The x-axis on both plots is the amount by which the state is deformed. So when the deformation parameter is 0, that's the ideal state. Yeah. And as you increase the deformation parameter, that's perturbing the state more and more. The y-axis is how often you're winning. Yeah. The shaded region is, well, so this line is 3/4. The shaded region is when you're winning with better than classical probability. And as long as you're in the shaded region, you're outperforming any classical strategy. Now, let's take the ferromagnetic game. So here, I should say solid lines are sort of theoretical prediction. Dotted lines are the actual data on the device. Yeah. So green here is you play the ferromagnetic game with 4 qubits, 9, 16. And you can see that you have a very rapid fall off in performance. Yeah. So as you make the system size larger, you can tolerate weaker and weaker deformations. And staring at this, at least I'm convinced that you take n to infinity, and the moment you deform even epsilon away from the ideal state, you'll cease to outperform the best possible classical strategy. Yeah. Now let's play the topological game. Red is 9. Blue is 16, and they're basically lying on top of each other. Yeah. So you can sort of pretty clearly see greater robustness of the topological implementation. Yeah.
So this is definitely some point you drive a phase transition.
Right.
Find phase what the.
Yeah, so here you do lose advantage before you hit the phase transition, right? So you outperform the best possible classical strategy over some non-zero fraction of the topologically ordered phase, but not all the way up to the thermodynamic phase boundary.
Trying to understand what I guess the benefit in this case of using the actual hardware was. You would not be able to compute these even with 9 qubits.
No, you could.
Right.
Yes.
But it's cute.
Yeah, because it's cute.
And then can you generalize, I mean, because they're obviously limited in number of qubits, so. But if you're interested in the large size behavior of this model.
Yeah.
I mean, I guess you're still, as far as I was from understanding that limit. Because you could only simulate up to the size.
No, I mean, you can only simulate as big of a device as they have. But analytically, I mean, we have predictions for how it should behave for arbitrary n, which agree with the actual devices for the sizes that are in existence.
But
Yeah.
using the machine, I mean, you already had a more powerful model.
Yes. Yeah.
Okay.
Natasha.
So physically,
Yeah.
the machine is the same on the left plot and on the right.
Yes.
So basically, you are just playing different games.
Yes.
And the only thing what you are showing that if I play this kind of games,
Yeah.
then what? You just show that this device is more quantum or basically.
No. So the strategy is robust,
Yes,
to perturbations. Yeah. Yeah.
Saying how good is the machine or not.
No. No. So I mean, one strategy is I prepare the.
It's a physical machine. It has some perturbation in the physical machine. I don't know, something is not working.
Right. I mean, okay, so I mean, that's in zero, right? So you could ask actually, so no, analytically, you should win with certainty if there's no deformation. Yeah. You look at the actual machine and they're not winning with certainty, they're winning with probability a little bit less than 1, right? And that's because the machine is not perfect. Their actual state preparation is a little screwed up. And in fact, like how imperfect it is varies from day to day. So my understanding is that they monitor the performance of their qubits and it fluctuates, and sometimes it drops below some threshold, and then they take the qubit out of the device and they fix it and put it back. I don't have to deal with any of that, but
why is that
Yeah.
limit then so much different for the GHZ inventory?
yeah, because the GHZ state is not subject to an orthogonality catastrophe. So even small imperfections in state preparation, as the system gets bigger and bigger, they mount up exponentially rapidly. So this is, you make the all zeros plus all 1 state, and then you try and play the sort of the GHZ game. And this is, you make the toric code state, and then you try and play the toric code game. And here you're much less sensitive to any.
So even without this deliberate.
Yeah.
Perturbation data.
Right.
you do worse.
Yeah.
I think that that's just a question can be rephrased as.
Uh-huh.
So what is the utility of the whole direction you're talking about?
Okay, sure.
If you
So
can.
one utility could be, you could view this as a way of characterizing topological order on quantum hardware. Yeah. So suppose somebody tells you that, I have made, Z2 lattice gauge theory, or I've made, I don't know, like Fibonacci anyons, or whatever your favorite topological order is on a quantum hardware. How do you verify this? Yeah. So this is one possible answer. If somebody tells you, I've made a toric code state, or Z2 lattice gauge theory on my quantum hardware, and you want to verify it, you go and you ask them to play this game, yeah, and you see if they can win this game in the thermodynamic limit, or at least if they can continue to win this game without degradation as you make the system size larger. Another answer, of course, is here is a task which you can now robustly do with access to this device, better than you could ever have done classically, even with access to infinite computational resources. Now, why would you want to win this particular game? I don't know. I mean, I sort of spitball, like what are other contexts where this sort of thing might be useful? Well, maybe you have some sort of traffic routing problem where, if everybody takes the same road, traffic gets really bad. If they split up, then it's better. But, and they can query this quantum state for which way to go. But why not just have a central planner like Google Maps tell them which way to go? I don't know.
But my
yes.
question was,
Yeah. Right.
do they appreciate
Yeah.
what they do, what you do? I mean, guys who making this device,
Yeah.
do they appreciate your device? or
Right. So
whatever?
at least, the guys that I worked with
Yeah.
appreciated it.
Yeah.
Do their bosses appreciate it? I don't know.
No, that's the guys you work with.
Yes, yeah. So they liked it, but they're physicists. So yeah. No, somewhere up the chain, there'll be a businessman. Does he appreciate it? I don't know. Yeah.
So let me try to understand sort of on the same lines of question.
Yeah.
So if I've understood correctly,
Yeah.
you've got an analytical solution here.
Mhm.
So in some sense, that's the answer, right?
Yeah, sure.
So you're putting this on a system.
Yeah.
Is there any possibility whatsoever that something surprising shows up?
Right.
And
So
that's
the main thing that could have happened is, I mean, so we think we have an analytic answer, right?
Yeah.
It's always possible that we screwed up, right? Or we missed something that was important. So you do it on the actual device and okay, it doesn't look like we missed anything.
So you're validating.
Right. Yeah.
But you could have validated in class.
Yeah, you could
I
have.
mean, this
Yeah,
is
sure. Yeah.
the question of the state of the art of the hardware.
Yeah.
Now, I was just gonna provide a whimsical answer to your question about you. Thinking about it, right?
Speak up, please.
You can, I mean, you have a game, right? And
Right.
You could ask, well, this is for many who cares about, right? It's useful for practitioners, but
Right.
Right, but then if you can imagine, some kind of betting system, right?
Right.
And if people believe they can play the game better than that, there you go.
Right. Yeah. Okay. Sure. Quantum casinos. Yeah. That's right.
Very quickly about the same.
Yeah.
So you said that you take a particular deformation.
Yeah.
The one that you can treat analytically.
Right.
What about generic one? Did you try any deformations that you cannot treat analytically and then the picture will be?
Yeah, no, we did not, because essentially we only had so many runs on the device, and this is what was easy to do. We think it should work because essentially the topological order should be robust and the braiding statistics should be robust. But no, we did not.
Look, I think it was kind of like, the obvious guess would be that you lose your advantage when the correlation length.
Yeah, it becomes large compared to the size of the loops.
compared to the size.
Yeah, exactly.
Presumably, that's what's going on here, and presumably that's what you would expect.
Rahul,
Yeah.
We keep bombarding you with questions.
Yeah.
How much time do the approach there for?
I can maybe just hit the highlights here. Okay, so toric code states, okay, are contextual. They can be used to robustly win. No, I think we're okay on time. Yeah, they can be used to robustly win this quantum game, which we've sort of demonstrated semi-experimentally. And yeah, as I said before, you could use this as a way to characterize topological order on quantum devices, and also as a successful demonstration of robust advantage at a particular fixed target task. And we're doing better than you could ever do, even with infinite computational resources at your disposal, if you were limited to doing classical physics. Okay, now you could wonder, what is special about toric code? And the answer is nothing. Yeah, so we think you should be able to define analogous games for any topologically ordered state with non-trivial braiding statistics. Yeah, so you could view this as a general purpose approach to the characterization of topological order on quantum devices. So if you really want to get Fibonacci anyons, somebody tells you they've made a state with Fibonacci anyons on their device, you know sort of what to ask them to sort of verify if they have or they do not. Yeah? And in fact, we've identified the appropriate games for 3D toric code, for the X-cubed fracton model, for the double semyon model, and for each of these, there are different games, but they're all using the same basic idea of sort of exploiting the braiding statistics in order to get advantage at a certain task. And we sort of what?
How do you optimize, like, you have game for 3D toric code,
Yeah.
game for X-cube?
Right.
What properties are you matching?
Can I defer answering that for one slide? Yeah. So we have an algorithm that sort of spits out a game for a broad family of topological codes. What is that algorithm? I'll tell you on the next slide. And yeah, this could be a powerful and general way to characterize topological order on quantum hardware. And how do you come up with this strategy? Well, there's a very nice unifying perspective, which allows you to do this. And that's to note that essentially all the known games, or all the games that I know of, now use as resource states something that spontaneously breaks symmetry. So like all zeros plus all ones is spontaneously breaking a global Ising symmetry. The toric code state is spontaneously breaking a higher form symmetry. So higher form symmetry is, well, we're used to thinking about global symmetries with the symmetry operator acts everywhere in space. We're also used to thinking about gauge symmetries with the symmetries act on points. Higher form symmetries are intermediate between the two. They act on deformable manifolds of dimension less than the dimension of space. Yeah. So for the 2D toric code, the higher form symmetries act on arbitrary loops. For 3D toric code, it's on arbitrary loops or arbitrary membranes. And all known games use resource states which spontaneously break some symmetry, either global or higher form. And all known strategies work in the following way. If the player is queried with a 0, they measure part of the symmetry operator. And if they queried with a 1, they measure part of an operator which is charged under that symmetry, so that it has long-range order in that symmetry breaking state. Yeah? And all the players together collectively end up measuring the twist product of a symmetry operator with an operator charged under the symmetry. Yeah? Now, if the symmetry at your disposal is global, yeah, then you need to measure a global operator because the symmetry operator is global. And any global measurement is subject to an orthogonality catastrophe. If you deform your state even a little bit, then no, your sort of overlap with what you wanted to get and what you're actually getting is exponentially small in system size. But if you have at your disposal higher form symmetries, yeah, then you can construct the game so that you're measuring twist products of entirely local objects. Yeah? And if you're constructing twist products of local objects, there's no orthogonality catastrophe. Yeah, there's just some finite degradation, but as long as it's not so big that like, you're doing worse than classical, you're okay. So that's that's your answer, Hart. You take your topologically ordered state, you identify the higher form symmetries, and once you've identified the higher form symmetries, that dictates for you what your game strategy should be. Okay, yeah, so the key is to use higher form symmetries to get these almost local twist products. And we can understand all known games and their robustness in this way. Some open questions. This topological strategy, it gives advantage away from the fixed point, but that advantage does not, well, firstly, you don't win with certainty away from the fixed point because there is some degradation, and you don't win all the way up to the thermodynamic phase boundary. So you could wonder, can you win with certainty away from the fixed point? Can you win all the way up to the thermodynamic phase boundary? Probably these things are possible, but likely they involve incorporating some amount of error correction. So that's not something we've done yet. But also, like way back at the start of this talk, I said that what really makes states quantum is contextuality. Yeah? Is there a way to operationally quantify contextuality? So that, well, okay, this is not yet published work, but we think we have an affirmative answer. Yeah. So what we tell undergrads is that what makes states quantum is entanglement. And entanglement has a nice quantification in terms of entanglement entropy, but entanglement entropy is not measurable, and also is this necessary but not sufficient thing, right? Where it's not directly useful. Contextuality is much more directly useful and measurable, but at least as far as I know, not known how to operationally quantify this. And we think that it should be possible to do this with games. Yeah. So first you need to know something about the game. In particular, you need to know what is the optimal classical win probability. And that can be done with various methods from Boolean mathematics. Specifically, it's quantified by something called the Walsh-Hadamard spectrum of the nonlinear Boolean function that's being computed with the game. Then we need to know what is the optimal victory probability given access to a certain quantum resource state. And the difference between those two things, optimized over all possible games, provides a quantification of many-body contextuality. Yeah? And optimized over all possible games might seem like very demanding, but actually all you need is that there is, you need to find a game which sort of wins with certainty, or like the optimal game, and that choice can be guided by knowledge of the symmetries of the state you're using. Okay, so to conclude, quantum games provide a powerful new perspective on many-body physics on quantum hardware. They give us a way to leverage the correlations inherent in phases of matter to secure definite quantum advantage at a given task. We've demonstrated this on an actual device, And there's this nice unifying perspective based on symmetries and evaluating crisp products of symmetry operators and operators charged under the symmetry. Yeah. Outlook, well, it would be interesting to bring in error correction, to have a way to quantify contextuality, to use this as a new kind of probe of order on quantum hardware. But at the end of the day, maybe I'll just sort of end by saying that this is a very powerful framework for thinking about many-body physics on quantum devices. And I think there's probably sort of many ways of applying this framework that have still to be developed. That'll conclude.
During the talk, I have many more.
You started from asking how can you define phases,
Mhm.
finite size device.
Yeah.
Transfer.
Yeah. Right.
What's the answer?
So I think you can at least define topological order on a finite size device by asking if you can play this game or an analogous game in a manner which outperforms the known classical bound. And it does so without degradation as you make system size larger.
Topological is either it exists or it doesn't exist.
Yes.
It's not like different phases. Each
Well,
with-
but different kinds of topological order have different games.
Did
so-
you try different topological orders?
Not on the device, but
Yeah.
analytically, yes. So there's one game which works with which uses toric code resource states. There's a different game which uses double Sunny-on states. A third game which uses X cube states. So if you think you have a particular topological ordered state, then you can verify that by playing the appropriate game. And the toric code game will not work on the X cube state. The X cube game will not work on the toric code state.
I mean, look, this quantum game is something like all the parameters to detect is the particular topological things.
So I didn't understand the question.
I was asking, so if someone give you a state.
Yeah.
And you don't know what it is, you want to know what kind of phase it is. So you use your game to play with it.
So you're saying if you're handed a completely a state and you don't know anything about it, can you go characterize it using quantum games? That would be challenging for many reasons. One of them, of course, is you need many copies of the state because you need to be able to play this game many times in order to get statistics. Okay. Yeah, so I mean, without any knowledge of what's going on, like how would you know the right game to try? I mean, maybe there's a way to do it, but I don't know what it is. So here I'm always starting with at least some guess as to what the state is supposed to be, right? So it's like somebody is telling me, I think I've made toric code, or I think I've made X cube, or I think I've made double Semyon. And maybe they have, maybe they haven't, but that at least guides the choice of what game to try and play.
Yeah, just 1 second. 1 second. There's
Right, I was wondering, is there a classical contextuality? So if you say shop for airline tickets, and
Right.
There is all in business class, but there is one in the economy, and the two people are shopping, and the
Right.
first one buys it,
Right.
then the second one will have to buy.
So, but there you,
A business class ticket and the vice versa.
so there you're allowed non-local communication. Right. So that's the key thing. What quantum mechanics does via contextuality cannot be reproduced in any classical model without non-local communication.
okay, very last question.
So in this context, when you say quantum advantage, I guess you mean you're able to solve some task with some greater ability than any classical model. Typically, at least in most talks, and when I see people who are quantum advantage, they're talking about they're talking about some sort of like speed up. So they have a particular.
They're talking about quantum computational advantage.
Yes, I guess the question is there any association between the two? And then maybe moreover, like I didn't see much discussion on like the actual runtime of the strategy you use in your game.
Yeah.
Like, can you say like connections between computational advantage
Yeah.
and this?
So I would say it's a different notion, right? So I mean, this is advantage at a coordination task. Usually people are talking about advantage at a computational task, right? I would say that the literature on advantage at computational tasks has two problems. The first is much of it is based on complexity theoretic conjectures, right? And so it's not really proven if you're outperforming. And maybe you can factor efficiently classically, right? There's no proof you can't do it. The other part is that it's very dependent on, like, you're doing better than any known classical algorithm, but tomorrow somebody else comes up with a better classical algorithm, and so it's sort of conditional on a particular set of classical algorithms to compare to. This is not, we're not trying to do any computation. Like, we're trying to enable players to coordinate without communication. Yeah. So it's a coordinational advantage, but at this coordinational task, we have an unconditional advantage, right? So they're doing better than any purely classical players could, even given access to infinite computational resources. Right? As for your other question about what's the runtime, all of this can be done in finite depth circuits. So the circuit depth that you need to implement does not scale with system size.
No, thanks very much. Thanks. You know who's next.